Hi everyone, Dr. Mike here. In this video, we're taking a look at vitamins. We're doing an overview. We're looking at all the different vitamins within the body, their sources, so where we can get them from our diet, but also other means, and also what their functions are within the body, and what can happen if we don't have enough. Let's take a look. All right, so to begin, we need to define what a vitamin is. A vitamin is an organic compound, meaning it's carbon-based, right? And we require it for survival. It's essential. So if we were to write down very quickly here, some important points, vitamins are essential for survival. Now you could argue, well, yeah, so are proteins, fats, and carbohydrates. Okay, another definition of a vitamin is that we need them in small quantities. So we require them in small quantities. Now this is quite different to the proteins, fats, and carbs, where we need to ingest them en masse basically to produce ATP and the various building blocks of the body. We need small quantities of our vitamins. Another important point here is that without them, we get disease. So deficiency results in disease. Deficiency results in disease, and ultimately death can occur. Another important point here is that we cannot synthesize them. We cannot synthesize vitamins. And that's another important point because to some extent we can synthesize proteins, fats, and carbohydrates, or at least some of their derivatives, but we cannot for the vitamins. So they're essential, we need them for survival. Without them, we get diseases. We need them in small quantities, not large quantities, and we cannot synthesize them ourselves. So we've now defined what vitamins are. Let's take a look at the different vitamins of the body. So you can broadly classify vitamins into two categories. You've got your fat-soluble vitamins. Let's write these ones up on this side. We've got our fat-soluble vitamins. And you've got your water-soluble vitamins. Now, why are they called fat-soluble and water-soluble? Well, probably makes a little bit of sense when you look at it. The fat-soluble vitamins, they dissolve, they mix in with fats really well. So lipid-based products, okay? Now that's important for a couple of reasons. It's important for a couple of reasons. One is this. It's important because they can get absorbed with dietary fat. They get absorbed with dietary fat. So think about that. Triglycerides and cholesterol, when we ingest them in the foods that we eat, they all come together with the fat-soluble vitamins and we can absorb them across into our bloodstream or our lymphatic system. That's important. So we can absorb them en masse with our fat-soluble substances from our diet. The other thing is they're stored quite well, predominantly in the liver, and they can be stored for relatively long periods of time. Each one's quite different in regards to the length that it can be stored, but generally speaking, we store them longer than the water-soluble. And that's important because water-soluble vitamins, they don't get absorbed with the fats in our body. So the water-soluble vitamins need transporters or channels for absorption. And number two, are not stored for very long, which means you can run out of the water-soluble vitamins a lot faster than you run out of the fat-soluble vitamins. Now let's take a look at what those fat-soluble vitamins are. Let's start with the fat-soluble. So you can remember them through DECA. D, E, K, and A. They're the fat-soluble vitamins. The water-soluble vitamins you can remember as the B vitamins, so the Bs, and there's 8 different B vitamins, and vitamin C. Let's take a look at the fat-soluble vitamins first. Vitamin D, E, K, and A. Let's go through them one by one. What they do, where they can be found dietarily, or whether we can maybe get them from some other means. So let's start with vitamin D. Vitamin D. All right. Vitamin D, its active form is called calcitriol. So its active form is called calcitriol. It's actually got another name, pretty terrible name, which is 1,25 dihydroxy vitamin D3. So it can be called calcitriol or 1,25 dihydroxy vitamin D3. Whew. Now, how do we get calcitriol? Well, we can get it in two forms. We can get it as vitamin D2 or as vitamin D3. Now, vitamin D2 is predominantly from our diet. So if we have a look at vitamin D2, so vitamin D2, its name, so it's got another name in addition to D2, is ergocalciferol. Ergocalciferol. And we can obtain this from our diet. So we can get this from fatty or oily fish. And if you ever think about what some fatty or oily fish can be, this can be salmon, tuna, right? Mackerel, for example. But we can also get it from fungi. And to a lesser extent, we can get it from certain animal products. So we can get it from egg yolks. We can get it from beef liver, right? We can get it from cheese. So these are the dietary means that we can get vitamin D2. There's vitamin D3, right? Now, vitamin D3, so let's write it like this. Vitamin D3, it has another name. Its other name is cholecalciferol, right? Ergocalciferol, cholecalciferol. Now we can obtain vitamin D3 through the same sources, right? But the vast majority of vitamin D3 is obtained through sunlight. So we get this through sunlight, specifically through UV. So you know the sun emits UV radiation, and there's UVA, UVB, for example, UVB. And what this UVB does is it hits our skin, and in our skin it turns cholesterol into vitamin D3. It turns it into vitamin D3. Now, what can happen here is this. We still don't have our calcitriol yet. We've got ergocalciferol D2, cholecalciferol D3. We need to create calcitriol, which is 1,25 dihydroxy vitamin D3. So what happens is these two products, D2 and D3, they need to jump into the bloodstream. So let's draw up the bloodstream here. Here's our bloodstream. They jump in, and in our bloodstream, we've now got vitamin D2 and vitamin D3. So from the bloodstream, it travels to our liver, right? So here's now our liver. And our liver has enzymes that turn vitamin D2 and D3 into what we call 25 hydroxy vitamin D3. 25 hydroxy vitamin D3. That has another name, calcidiol, right? So that's also called calcidiol, not calcitriol, calcidiol. There, so the liver's turned D2 and D3 into calcidiol. The liver then hands it over to the kidneys. And the kidneys itself, right? Here's the kidneys. The kidneys itself has enzymes that turn the calcidiol into calcitriol, which is the 1,25 dihydroxy vitamin D2. Whew, mouthful. Calcitriol. Now, what the kidney can do with this calcitriol, release it into the bloodstream, and what does calcitriol do? So the active form of vitamin D. Calcitriol can, let's write this in a different color, increase calcium and phosphate absorption. And this is obviously happening in the intestines. So calcitriol can increase calcium and phosphate absorption, which means it can increase blood calcium levels. That's very important. What else can it do? It can increase bone mineralization. So it's very important for bone health, right? Bone Mineralization. Have I spelt that correctly? Yeah, that's good enough. And it does this by activating osteoblasts. So remember, your bone is constantly being remodeled, built up, broken down throughout the day, right? And throughout your life. It's being built up through osteoblasts, think of the B, osteoblasts build bone, and it's broken down through osteoclasts, think of the C, osteoclasts crush bone. Calcitriol stimulates osteoblasts, helping throw the calcium that we've just absorbed into the bloodstream into the bone, increasing mineralization. It can also increase, calcitriol can also increase renal reabsorption. So it's saying don't pee out the calcium, reabsorb that calcium back into the body. So obviously vitamin D is really important for our blood calcium levels. Okay, it also plays a role in immune function, and it can help regulate or modulate immune function, but the specifics of that aren't well elucidated. So these are the main functions of vitamin D and the sources that they can come from. Let's now take a look at the second one, vitamin E. So let's get rid of this at the moment and have a look at vitamin E. Vitamin E. Now vitamin E has another name. Its name is alpha tocopherol. Alpha tocopherol. And alpha tocopherol, it can be obtained through a number of important sources. So one important source here for alpha tocopherol are the whole grains, vegetable oils, seeds and nuts, right? So let's write this down. Seeds, nuts, vegetable oil, and whole grains. Whole grains. So these are the places that or the sources that we can obtain vitamin E. The active form, alpha tocopherol, what does it do? Well, it does a couple of things. One is it is a potent antioxidant. A potent antioxidant. Specifically, this is important for polyunsaturated fatty acid oxidation. To stop, I'll write it like this, polyunsaturated fatty acid oxidation. And you might be sitting here looking at this going, I don't know what that means. I don't know what a polyunsaturated fatty acid is. I don't know what oxidation is. Effectively, oxidation is the loss of electrons. You can remember it like this, Leo. The loss of electrons is oxidation. So, all the body is made up of the various atoms and elements of the periodic table, and they've all got protons and electrons, right? If we take the simplest one, hydrogen, the first on the periodic table, hydrogen, right, is simply made up of a proton and a negative electron that's sort of flying around the outside effectively, right? One proton, one electron. If I were to steal that electron, I've just oxidized hydrogen. So the loss of electrons is oxidation. Now, the problem with this is it makes a molecule hungry for electrons, right? If you steal an electron, it's not complete. It's going, I need to now find an electron somewhere. And that's a problem because it'll just go to various tissues of the body and steal electrons. So importantly, what can happen is that our polyunsaturated fatty acids are very prone to being oxidized, to having electrons stolen from them. And I'll tell you as briefly as I can the reason why. So firstly, what is a polyunsaturated fatty acid? If I were to just draw up a fatty acid effectively is a hydrocarbon chain, which means there's a whole bunch of carbons, right? A big carbon chain, and those carbons are all bound up to the hydrogens. And you can see each carbon has 4 bonds associated with it, right? Look at that. Each carbon, let's take this one, has 1, 2, 3, 4 bonds. That means it's complete with its 4 bonds. This is what we call a fatty acid, right? A fatty acid. Particularly, you'd call it a saturated fatty acid because all the carbons have 4 separate bonds. Saturated fatty acids. These are nice linear fatty acids. Now, if we want to make a fatty acid saturated, we need to introduce a double bond into the mix. So for example, if I were to put a double bond here, there's now an uneven amount. Now there's 5 bonds, right? 1, 2, 3, 4, 5 for this carbon. We can't do that. So we need to get rid of a hydrogen bond. And the same thing would happen for this one. We'd need to get rid of a hydrogen bond. Now what we've got is all these are saturated, but this is what we call unsaturated. This is an unsaturated fatty acid. Now if you have a polyunsaturated, there's just more of these double bonds, right? So let's make this a little bit longer and have a look, right? So let's just say we've got that, and let's put another double bond here, and then we'll finish it here, right? So what are we going to have? We're going to have, this one's going to have hydrogen here, this one's going to have hydrogen here, and then it's all filled up because each one now has 4 bonds. This is what we call a polyunsaturated fatty acid. Now what I haven't shown you, because that's where it's unsaturated, these double bonds put kinks in the fatty acid. It puts it at an angle. And the importance of this means that at room temperature, right, if it's linear, these fatty acids stack on top of each other and they become solid at room temperature. But if you've got these saturations in it, or unsaturations, sorry, and you now become polyunsaturated, they've got kinks in it, they don't stack on top of each other very well, and it remains a liquid at room temperature. So polyunsaturated fats are liquid at room temperature, right? Think about vegetable oil, that's a polyunsaturated fat. Olive oil, polyunsaturated fat. Now, what I'm telling you all this is because when you've got a double bond put in, the electron cloud, right, that sits around molecules becomes unstable. Well, not unstable. What it does is that the electron bond here between the hydrogen and the carbon, it starts to sort of pull away the electron field, right? And here it happens as well. Where the double bonds are, it disrupts the electron field. And that means that the carbon and this hydrogen bond here becomes weak and unstable, which is perfect for when we have certain molecules that come along that want to steal the electron, for example, from that hydrogen. Now, these are called free radicals. Now, free radicals, an important free radical, for example, is hydroxyl. Now, hydroxyl is a free radical that's produced through the electron transport chain. It's produced through other forms of metabolism, through UV radiation, a whole range. So the body's always producing free radicals. So to a degree, they're normal, right? Now, if I've put a dot here, that means it's hungry for an electron. And what it does is it searches through the body and finds polyunsaturated fatty acids and sees this unstable hydrogen and decides to steal the hydrogen. So if I were to draw up this whole thing here like this, that whole lipid molecule, right, I'm going to write as R, and then the unstable hydrogen I'm going to write like that. So when this comes across this polyunsaturated fat, what does it produce? It steals the hydrogen, which comes with an electron, right? And so it now becomes stable, because I said it's hungry for an electron to become stable. So that hydroxyl free radical has now become water, stable. But what has this thing now become? Well, it has now become, if I move out the road a little bit, an unstable lipid. This is now a lipid radical. Uh-oh, what's this lipid radical do? Well, this lipid radical will come across oxygen. So we know we've got a lot of oxygen in the body. So it comes across oxygen. And what does it produce? It produces ROO. Ooh, it's still a radical. It's now what we call a lipid peroxyl radical. A lipid peroxyl radical. It's still going, it still wants to steal electrons. Now, this is going to come across other unsaturated, polyunsaturated fats, and it's going to try and steal the hydrogen from it. Now, if this steals the hydrogens, right, from an RH, so let's say we've got a nice RH here, and it comes across it, what's it going to do? So we've got the RH here, comes across, it's going to steal the hydrogen, right, to become whole again. It's all good now. So instead of being a lipid peroxyl radical, it is now stabilized. And what has it produced? What do you think it's now produced? It's now produced another of these radicals, another radical. So the offshoot is another radical. Now that, what do you think is going to happen? It's going to get oxygen again, and it's going to steal more hydrogen. So the whole process starts over and over and over again. And what this is called is lipid peroxidation. So lipid peroxidation happens over and over and over again. And you get this chain of events where all the polyuns, if you have too many free radicals, the polyunsaturated fatty acids just become oxidized. That damages obviously the fats which make up membranes of the body and a whole range of things. So what do? Well, we have alpha tocopherol that comes along. Now what alpha tocopherol does, let's draw this in red. So here's alpha tocopherol, and it has, thankfully, a spare hydrogen. And it says to this lipid peroxyl radical, no, don't come and steal the hydrogen from our normal, polyunsaturated fat. I'm going to give it to you. So it gives that hydrogen, producing the satisfied free radical by bypassing making more free radicals from polyunsaturated fats. But what is end up remaining from this is the tocopherol is now a radical. But the thing is, vitamin E, alpha tocopherol, is far more stable than the lipid peroxyl radical. It's far more stable than other radicals. So it can steal that and not be damaging and not want to go steal electrons from others. I'm going to talk about later exactly what happens here as well, because vitamin C is involved in this process. So that's vitamin E. Let's now talk about vitamin K. So vitamin K is really important. It's got two major types. So you've got K1, which is called phyloquinone, and you've got K2, which is called menaquinone. So you may have seen the vitamin K as being referred to as the quinones, right? The active quinones. Now where do we get vitamin K first of all? So vitamin K1, vitamin K2. Vitamin K1 we obtain from our diet, and you can get it from leafy greens. You can get it from cabbage. You can get it from things like, so leafy greens, cabbage, cauliflower. So these are some of the major contributors to where we can obtain our vitamin K1 from. Now vitamin K2, we get vitamin K2, it's actually synthesized by our gut flora. Vitamin K2. So we don't obtain vitamin K2 predominantly from our diet, we get it from our gut flora making it, so in our intestines. So what does vitamin K do? So it does a couple of different things. Firstly, vitamin K is really important for clotting. Now, how does it do this process? So if you have, for example, if you've got a blood vessel, and let's say this blood vessel is damaged, right? The last thing you want is to bleed out. Last thing you want is for blood to leave. Lose blood volume, lose important products. Not a great thing. So we need to block this up. Now we know there's what's called the clotting cascade, but we also know a couple of things happen before the clotting cascade or immediately before the clotting cascade kicks in. You have vascular spasm, so the blood vessel constricts or contracts, right? You have platelets aggregating to the site, right? Which sort of forms a plug. And then you have the clotting factors which are made from the liver coming along. Now there's a whole range of clotting factors. If you want to watch a video on the clotting cascade, I've done that. I'll put the link in the description below, or Google Dr. Mike clotting cascade. Effectively, the clotting factors, so the clotting factors are made by the liver, most of which are made by the liver, and they need to come along and trigger a cascade of events that cause ultimately fibrin which are strands to mesh up this area, basically forming a net, a mesh to block any excess bleeding. That's what we call the clotting cascade resulting in coagulation. How does this happen and what does vitamin K do? So, you're going to have, effectively, collagen fibers exposed when you damage a blood vessel. And collagen fibers are negatively charged. Now, platelets, which are coming past because we've got platelets in our bloodstream, they're going to start to stick to these collagen fibers because one, they're negatively charged, two, they're sticky, right? So we have platelets accumulating, sticking to this area. Now, to help the process, because platelets are also negatively charged, we've got something called von Willebrand factor that's released by the damaged epithelia and by the platelets, and they help tether them together. The negative collagen, negative platelets, you think they would repel, but the von Willebrand factor hold them together. It's like a tether, right? That's great. So now we're forming a plug, but now we've got clotting factors coming past. Now the problem here is clotting factors are made out of proteins, right? CF, they are proteins. And we know proteins are negatively charged. And the problem is negatively charged things won't bind to negatively charged things. So these clotting factors are at risk of just moving past and not clotting the area. So what we need is two important things. We need vitamin K and calcium. Now what vitamin K does is it carboxylates the clotting factors. So it adds basically carbon dioxide, right? Carboxylates the clotting factors. Now, if you carboxylate the clotting factors, COO negative, COO negative, COO negative, you're making it more negatively charged. And you might be thinking, wait, that's silly. I don't want it negatively charged, I want it positively charged. Vitamin K carboxylating it, making it more negatively charged so that the positive calcium can bind to it and act like von Willebrand factor in a way does and tether it to that site. So if all the important clotting factors are carboxylated, calcium in the bloodstream allow them to all accumulate here. And the cascade, the clotting cascade can occur where they all trigger each other to ultimately form fibrin and it blocks up. So effectively vitamin K through carboxylation allows for calcium to bind. And if calcium can bind, it tethers it up and clotting can occur. If you don't have vitamin K, you don't get these clotting factors becoming charged enough and it won't bind to the calcium and it won't bind to the site of damage, right? So that's important. That's one reason why we need vitamin K for clotting. The second reason why we need vitamin K is important here as well, is that sometimes people are at risk of accumulating calcium plaques in their blood vessels. So calcium can actually accumulate in the blood vessel and that can form plaques which obviously lead to atherosclerosis, heart disease, heart damage and so forth. What vitamin K can do is it, in addition to carboxylating clotting factors, it can carboxylate these proteins within the matrix, right? And so let's just say that is this important protein, it carboxylates it. And what it does is instead of telling the calcium, yeah, I'm gonna just embed myself in the epithelia here, the calcium instead will bind to these matrix proteins, reducing how much calcium is embedded. So that won't happen. You won't, or you get a reduced number of calcium being stuck to the walls of the blood vessel. And they bind up here so that it reduces that risk. So it allows for the vascularization or the blood vessels to reduce any calcium plaques that can occur or calcium deposits occurring. All right, so that's vitamin K. So we've done D, E, K, we now need to do vitamin A. So I'm gonna leave this one up because I need this for vitamin C. Let's do vitamin A now. Vitamin A is important because you can get it in two forms as well. So you can get vitamin A from animal products and you can get vitamin A from plant products. Now the vitamin A we get from animal products can include things like, might as well write it down, egg yolk, butter, liver, fish, and so forth, right? The plant products, you can get it from basically the plant products that have a yellow or reddish or orange coloration to them. So think about carrots, think about pumpkin, but you can also find it in your leafy greens as well. Now, what's the difference between these two vitamin A's? So what you end up getting here is that you can have from the animal products, you get what's called retinol. Let's write it here. Retinol. Basically, it's ready to be used, retinol. The animal product's ready to be used. What we get from the plant is what we call the carotenoids. Often they're called the carotenoid pigments. Hence why they've got those particular colours. What we effectively need to do is, if we take the carotenoids, and send it to the liver, send it to the intestines will convert the carotenoids into retinol. And what that retinol will do is that retinol will go to the liver. So let's draw the liver up. That retinol will go to the liver, and it can either be stored here, right, because it's fat soluble, so might be stored, or it's going to be bound to a carrier protein, which the liver mostly produces, plus a protein for carrying. And then we'll throw it into the bloodstream. And where's it going to send it to? It's going to send it to the eye. So we've got retinol traveling to the eye. Now, if I were to draw the eye up, we're going to have, obviously, you know, the front of the eye with the lens and the pupil, but we're going to have the retina at the back. So there's going to be a number of layers at the back. Now we need room for that optic nerve to travel down, but here we've got the retina at the back, and there's a couple of different layers. First, now I'm not going to go through the specifics of the layers, but importantly, this layer that we're referring to first, this is an epithelial layer, right? And so the retinol gets sent first to the epithelial layer. So this is epithelia of the retina. Epithelia of retina. And what the epithelia of the retina does is it turns, if I can spell it correctly, retinol into 11-cis retinal, right? Retinol into 11-cis retinal. Then what happens is you now have an area that has rods and cones. So you've got an area that's got all these rods, and you've got an area that's got all these cones. They're really important for vision, for sensing light, and for transducing light signals through the optic nerve. Now this 11-cis retinol predominantly gets sent to the rods. And what happens is at the rods, it can turn the 11-cis retinol by binding it with something called opsin, which is a light-sensitive protein, to form rhodopsin. And this rhodopsin can go into both rods and cones, and it's waiting for light to come in through the eye and hit the rods and cones. When it hits the rods and cones, it activates rhodopsin. So when light comes in, it activates the rhodopsin and basically turns that rhodopsin into, well, the opsin comes off. It then forms trans-cis retinal, and that needs to be turned back into 11-cis retinal to be transported. And this whole process of light hitting it, activating the rhodopsin through a process that's probably more complex than I can understand, it then sends it transduces a signal via the rods and cones to the optic nerve that then goes to the brain and allows for you to make sense of the light that you've seen, right? So obviously, vitamin A, really important in this process, really important. So vision, probably the biggest function. Now, that's the fat-soluble vitamins, vitamin D, E, K, and A. Let's now take a look at the water-soluble vitamins, vitamin B, the B vitamins and vitamin C. So if we were to have a look, now, importantly, this is important. The B vitamins, right? There are about 8 of them. And I'm not going to go through them. And the reason why is because I've done a whole video on the B vitamins. So that's going to be in the description below. I talk about their function and exactly where they're located. But what I'm going to say here about the B vitamins is that all 8 can be obtained through both animal and plant sources. Animal and plant, not all, animal and plant sources. So obviously this is going to be, you know, meat, which includes fish. It's going to be eggs, milk, cheese, but also you can get it through, you know, leafy greens and other various vegetable products. So a balanced diet that includes animal and plant material will obtain the B vitamins. However, one important caveat here is vitamin B12. B12. Vitamin B12 can only be found from animal sources. So there are no plant sources for B12. So that needs to be obtained through meat, eggs, milk, cheese, things like that. So for those who are vegetarians or vegans, they may at some point become deficient in B12 without a supplement. So what do they do? What do the B vitamins do? Like I said, watch the video for the specifics, but they are involved in metabolism. So energy metabolism. Energy metabolism. So think about things like glycolysis, Krebs cycle. Now, Krebs cycle is important because all roads lead to Krebs. So, you know, you can have fatty acids jumping into Krebs, you can have glucose jumping into Krebs through pyruvate and so forth. You can have amino acids jumping into Krebs, but it's also reversible to a degree, right? And those amino acids from the Krebs cycle can turn into neurotransmitters. So also B vitamins are important for neurotransmitter production and a whole range of other things. Watch that video to get the specifics. It's too much for this video. Now let's finish off with vitamin C. What does vitamin C do? Let's get rid of this. First thing, where do we get vitamin C? Vitamin C has another name, ascorbic acid. Ascorbic acid. And it can be found in fruits predominantly, particularly citrus fruits, right? You've probably heard of scurvy before, which can happen if you don't have enough vitamin C. Damages the collagen. So obviously a function of vitamin C is appropriate collagen synthesis. That's part of connective tissue. And pirates used to get scurvy. So it was, you know, a pirate disease, or more specifically a disease of people who just did not eat their fruits because on long ship voyages, there weren't fresh fruit. And then they discovered, well, let's bring some limes and lemons, and also fermented products like cabbages, for example, can produce vitamin C, and that helped to prevent them from getting scurvy. So particularly citrus fruits, but also fermented vegetables can produce it as well. What does vitamin C do? All right, vitamin C, 2 important functions. One is collagen synthesis. Let's talk about that one first. Collagen synthesis. What is collagen? Connective tissue. You know that your body is made up of 4 major tissue types: epithelial tissue, nervous tissue, muscular tissue, but also connective tissue, which binds, wraps, and holds structures of the body together. Really important part of connective tissue is collagen, which are proteins that make things strong but also flexible as well. When you eat meat and you get that white gristly bit, that's collagen. Okay, very tough proteinaceous material. So we need it for normal body production. But the thing is, before we can make collagen, we have something called procollagen. And I said to you, collagen is a protein, so it's made up of amino acids. It's got proline and lysine amino acids associated with it. And importantly, these proline and lysine amino acids, they need to become hydroxylated before procollagen can become collagen. And what do you think does that? Vitamin C. Vitamin C comes along and helps hydroxylate. So hard for me to speak and write at the same time. Hydroxylate these amino acids to turn procollagen to collagen. Now we've got mature collagen, it's fine. Without it, you don't get mature collagen. All right, the second thing that vitamin C does is, again, it's a potent antioxidant. Now, when else did I say that? I'll give you a hint. Over here. So, I said that vitamin E is a potent antioxidant. When you've got your polyunsaturated fatty acid coming across a free radical, produces water, but now you've got a lipid radical. It's going to try and steal more hydrogens, and that's what it does. Once oxygen comes along, it becomes a lipid peroxyl radical. It takes a normal polyunsaturated fatty acid, steals the hydrogen to become whole again, and then becomes reactive and just keeps doing it. Luckily, we've got alpha tocopherol vitamin E, which can just hand it the hydrogen, so it doesn't need to steal it from the polyunsaturated fatty acid to make it stable. But it's ultimately just more stable, not completely stable. So what we get is, if we have alpha tocopherol, right, and it turns into a more unstable version, right, this is obviously a reversible reaction. What can happen is vitamin C, right? So you've got different forms of the vitamin C. And what can happen is, if you've got this form, the unstable version, the radical version, right? Vitamin C, which is reduced, right? Now you might be going, what the hell does that mean? So I said you've got oxidized and reduced. Oxidized means it's lost an electron. This one has gained an electron. And often we can do this with hydrogens, right? So that's what it did there. So that's the reduced form, that's the oxidized form. Here's the reduced form, that's the oxidized. So what happens is, vitamin C cannot regenerate vitamin E by handing it a hydrogen, right? And then that becomes an oxidized version. And you might be thinking, we're just passing the buck on. We're just making one thing a radical to make another thing a radical. Okay, so what can happen? Well, vitamin C basically can become whole again. So this process can become whole again through the use of glutathione, right? So glutathione can actually donate. So I'm not gonna do the whole thing, but glutathione is important in this process, and NAD plus / NADH is important, okay? They can also help this process of regenerating vitamin C back again. All right, so that's a quick run through of all the vitamins of the body and their functions. I hope that helped. Hi everyone, Dr. Mike here. If you enjoyed this video, please hit like and subscribe. We've got hundreds of others just like this. If you want to contact us, please do so on social media. We are on Instagram, Twitter, and TikTok at Dr. Mike Todorovic, at DrMikeTodorovic. Speak to you soon.